Many of us have heard about quantum mechanics and have been fascinated about the confusing and wonderful world it is. However, we are often daunted by its complexity, which often involves ideas beyond our common sense, as well as the mathematical analysis, which typically involves multivariable calculus, differential equations, as well as complex functions and many more. But as diverse as it might seem, all of the ideas in math or quantum mechanics is derived from something known as wave-particle duality. In order to understand wave-particle duality, let's take a look at what is so different between waves and particles. In a classical sense, particles such as grains of sand can be clearly located without any uncertainty in their position. Waves, however, are not confined to a specific location, and so they are spread out over many regions at once. For example, light from a light beam is spread out and is not found in an exact location. So why is location so important in quantum mechanics? Well, unlike our world, quantum mechanics is a world of uncertainty. While we are quite used to knowing that our favorite book can be easily located on our shelf, this is remotely the case in quantum mechanics. Imagine like when you went to your bookshelf, you found that your book was not at the place where you left it, but instead spread out over many different locations along the shelf. However, when you tried to grab one of the images of your book, all of the images disappeared, leaving you with your one book on a random location on your shelf. Wait, how is this possible? Of all the times I lost my pencil case, it was because it was located at an exact unknown location rather than it being located at multiple places at the same time. While it might seem strange to us, this happens to matter all the time at the quantum level. This is known as quantum superposition and can be explained by the dual nature of matter. When matter is not being observed, we cannot define its exact position. However, we can predict where the particle is most likely to be found. This uncertainty of a particle's location is similar to the uncertain nature of a wave, giving it wave-like properties. However, when we observe the matter that is currently in its wave state, it collapses back to the state of a particle. So in our example of the book behaves like a wave while we are not interacting with it. However, once we interact with it, it behaves like a particle and appears at one location only. So why is wave-particle duality so helpful in our quest to understand the quantum world? Well, all of the confusing and complicated theories are all based on the fact that matter on a quantum level can sometimes behave like a particle as well as like a wave interchangeably. This results in the phenomena of quantum superposition, which is able to account for the quantum phenomena we observe. So the next time someone tells you that they don't understand quantum mechanics, just let them know that it's all based on wave-particle duality.